we've seen that the condition that the eigenvalues must be real in order to represent real physical observables requires our operators to be Hermitian. That is something that we can now translate into some deeper knowledge about the eigenfunctions associated with those eigenvalues. So I want you to consider a Hermitian operator A, and that Hermitian operator will have a few eigenstates or eigenfunctions, and I'll write a couple of them here. So we'll have one eigenfunction that will be labeled by the label j, so it has an eigenvalue little a sub j, and another eigenfunction k with eigenvalue little a sub k. And so what I want to do is to take these two conditions. I'm going to take the complex conjugate of this one so that I can write this. And I want to combine these in such a way that it will give me some idea about the relationship between the eigenfunctions phi sub j and phi sub k. So how would I do this? Well, one way might be to make use of the Hermitian property in the following way. So I'm going to indicate that over here. So the Hermitian property would tell me that if I have an integral that looks like this, where I've got phi sub j star with the operator a and phi sub k, and I'm now integrating over all space and all coordinates, that because this is Hermitian, I must have the following equality. I must say that this is equal to phi sub k times the complex conjugate of the operator operating on this complex conjugate of phi sub j. All right, so this is the Hermitian condition as we have it. Now, on this side, the operator is operating on phi sub k, so I already know the result of that is to give me back the eigenvalue a sub k. So I'll write this down here. This part doesn't change. The operation of a on phi sub k will give me a sub k times phi sub k. Similarly, here I'm operating on phi sub j, and I've already taken the complex conjugate of this, so I can immediately write down that the operation here is going to give me the integral phi k. Now, a star on phi j star, as I've got over here, gives me a j star phi j star. And now, since they both obey the Hermitian property, these two things must be equal to one another. So this must be equal to this. But this is just a constant times some function, so I can take it out in front and arrange these two functions like this. And same thing over here. This is just a constant, so I can bring it outside the integral and write aj star times the integral phi k phi j star d tau. And now I'll point out that this is just the multiplication of two functions. All right, there's nothing special about that. There's no operation going on, so it doesn't matter which way I order the functions. The multiplication of functions is a commutative property. So this would be the same, this thing over here would be the same as phi j star phi k. So in effect, this integral and this integral are the same integral. But rather than go ahead and write them down that way, let me rearrange this equation in a different way. So I'm going to take this equation and rearrange it so that they're both on the same side. So I'm going to bring this thing over to this side, which allows me to write a sub k minus a sub j star times the integral phi j star phi k d tau. And now I don't have anything left on the right hand side, so that's just equal to 0. So here is a special condition that I have, and I've got a couple of different ways to satisfy this condition. Let's consider a couple of special cases. Let's suppose that j is equal to k. So in other words, this is the same eigenfunction in both cases. Well, since I know that aj star must be equal to aj if it's a Hermitian operator, which we have said that it is up here, then that means that this thing will correspond to ak minus aj, but j and k equal one another, so that must equal 0. So in the condition where j is equal to k, where I'm dealing with the same eigenfunction, this is going to become 0 because it has the same eigenvalues. All right, but what about when j does not equal to k? What about then? All right, well then we will, there's two possibilities. We could still have the eigenvalues equal, but I'm going to assume for sake of argument now that we have ak is not equal to aj, or aj star for that matter. So what that means then is that if this part cannot be 0, then the integral must be 0. So in other words, we must have this case. Oops, d tau equals 0. Well, this is basically telling us something about the relationship between these two eigenfunctions. And in particular, what it's telling us is that these two eigenfunctions have a property that we know of as functional orthogonality. And functional orthogonality results whenever I have two functions, let's say f and g, and I integrate them over all of the coordinates, and I get 0. So in other words, it is an outcome of integrating two functions, a product of two functions, and getting 0 at the end. Now, I'll talk in another video about what this means in terms of how we can visualize it. But one of the things I would challenge you to do as an extra little practice problem is that these are both eigenfunctions of the same Hermitian operator. So that means that anytime we have a Hermitian operator and there are two different eigenfunctions corresponding to different eigenvalues, that means that their two eigenfunctions should be orthogonal to one another. So I'm going to invite you to try this out with two of the eigenfunctions from the particle in a box. And I'll write down the very first one, which is, pi x over L. So this is the eigenfunction corresponding to n equals 1, and the eigenfunction corresponding to n equals 2 would look like this. And so you should use this kind of formula to calculate, and it actually will be for the particle in a box, 0 to L of the product psi 1 star psi 2 dx, and you should be able to show that this is equal to 0. Now, psi 1 is written as a real function, so you don't have to worry too much about the star. Psi star is the same as psi when it's a real function. But go ahead and see if you can evaluate this integral. You could use Wolfram alpha to do it, but you should be able to show that these two eigenfunctions of the particle in a box, because they are both eigenfunctions of a Hermitian operator, the Hamiltonian of the particle in a box, that their overlap, their integral of their product has got to be equal to 0, meaning that they are orthogonal.